Hello.
Yeah, good evening, sir. You're audible.
Yeah.
We'll start within
Yes,
2
sir.
minutes.
Shall we start now?
Uh, 2 minutes, within 2 minutes, we'll start.
Okay, fine. Thank you.
Very good evening to all. Myself, Dr. Preetham Kumar Das. I'll take this honor to invite you this ATAL online 6 days FDP, which is in the area of manufacturing industry 4.0. And this is the 4th day of our FDP and session number 7. So in this session, Dr. Umesh Kande is going to present this session, and he is our resource person for today evening. So I heartily welcome to all of you to this 6 days online of ATAL FDP program. And now I'll request Dr. Sandeep Kunar to give a brief introduction about the Dr. Umesh Kande. And within 5 minutes, we'll start the session. And our faculty also joining this slowly. So I'll request Dr. Sandeep to give a brief introduction about the Dr. Kande.
Good evening to all. Now I am going to provide the introduction about Dr. Umesh Kande sir. We are delighted to welcome Dr. Umesh Kande as a distinguished speaker for the AICT ATAL online FDP on AI and simulation in additive manufacturing. His academic and professional background: Dr. Umesh sir working as an assistant professor at the National Institute of Foundry and First Technology, Ranchi. And he is working as an assistant professor since June 2019. His academic journey includes a postdoctoral researcher at the Indian Institute of Foreign Trade, New Delhi, November 2018 to 2019. His teaching and research experience: he is working as an assistant professor in OP Jindal Institute of Technology, July to December 2012. He is working as an assistant professor, Guru Ghasidas Vishwavidyalaya, Central University, January 2010 to May 2012. And also he is working as a lecturer, Chowsky Engineering College, July to December 2009. And with his rich academic background, he has also contributed a lot in teaching, research, and industry collaboration. His expertise in advanced manufacturing and materials engineering makes him a valuable resource for participants in that FDP. We look forward to an insightful and engaging session with him. So I request you, and today's topic is optimization of machining parameters in context of Industry 4.0. So I request you, Dr. Umesh Kande sir, please continue your lecture.
Umesh sir, your voice, mic is off.
Thank you, Dr. Sandeep. It was a very nice introduction. So without any delay, let me start sharing my presentation. Along with that, I'll start dealing with the topics. My screen is visible to you all.
Yes, visible, sir. Yes, visible. Visible, sir.
Fine, fine. So today's I am Yeah, fine. Yeah, today's I'm dealing with the topic and that is optimization of machining parameter in context of Industry 4.0. So what we'll do, we'll start with some fundamental about the manufacturing related to its need, concept, how what was various types that has been evolved nowadays. In ancient times, some traditional manufacturing processes were used. Now it has been slowly started and becoming at the advanced stages or advanced level. So if we'll go with the some introduction or the concept that is related to your manufacturing, that is also known as in some cases, in some books or some author mention as a production. So what it is, generally it is conversion of raw material into a usable form. So why we need this manufacturing and what are the concept behind this? So basically in any country, when we'll see the prosperity and human civilization are mainly governed or judged by improvement and maintenance of standard of living of human being. So that is mainly just through the availability and production of whatever the quality goods you are having, as well as the services that are provided to the mains material welfare, as mentioned in the slide. So these not only related to your manufacturing industry, but it also covers various domains like housing, clothing, medicine areas. So there we will have some civilization from the ancient time to the recent times. How they are mainly judging the human civilization on the respect with your good quality product as well as what are the availability and maintenance which is leading to give you the good services and products for mains material welfare. So this mains material welfare depends mainly on availability of natural resources. Whatever we are having the resources freely available to us in the nature that we need to use, on that we have the dependency of this manufacturing. Next one, it depends, this mains material welfare depends on exertion of human effort both physically and mentally. Means whatever the effort we are going to put into the conversion of the raw material into useful product, that is ultimately having our physically involvement as well as mentally while conversion of those raw material into the useful product for the mains material welfare. So for magnifying this effort, we need some, that is tools. Those tools are nothing but it is the one kind of technology or one kind of these processes in terms of means you are going to facilitate to just accelerate the your human effort or which is going to magnify the human efforts. So if you'll see formula wise, it is main machine welfare equal to natural resources what we are having as in the form of air, water, heat, light, plants, whatever animals, solid, liquid, minerals, that will be multiply with your human efforts, how much effort you are going to contribute towards the development of prosperity of human being or for the human civilization, for the good life, standard of living you want to improve. So that has to be having raised power to the tool. So what is happening? This tool is nothing but it is going to magnify the human efforts. So tools refers to the power plant, chemical plant, steel plant, machine tools, which generally magnify the human capabilities. So this clearly indicates the important role of components, that is natural resources first, second one is human effort, and next one is the tools which is generally used for achieving the means material welfare and progress of civilization. Okay, coming to the next slide. So production or manufacturing, if you will define, that is what? As I said, conversion of raw material into the usable product. So this can be simply defined as a one value addition processes. So value addition means what? You are having a raw form of the material with you that has to be converted through the processes into the usable form. For that, you need to require the input. Input is nothing but whatever the energy resources you are using to convert this particular raw material, along with the processes through which it has to be passed and give the product that of the desired form, having the definite shape, dimension, surface finish, etc. That has to be with you after production. So here what is happening, let's you are considering one lamp of this material like mild steel or whatever it is in the H form. That is unusable form, having the low value, low surface finish, whatever it is in the raw form. So you involve some processes like turning to make it some bolt. So bolt is now having its thread on it. So what is happening? Some features you have provided, some usability is now clearly appear after the production of this bolt that can be used for some purpose for which it is fit. So then you can say this unused raw material is finally converted into some usable form, that is your output product in a desired shape, dimension and surface finish which you wanted to have after conversion of this raw material. So manufacturing processes, if you will categorize, that will be covered under these two, that is production or manufacturing processes. What are the processes or different kind of processes that actually involves during the conversion of these raw materials or whatever you are having with you, which you wanted to give some values in it. So what will happen after conversion? It can be easily usable to the human kind for their prosperity. So next one is the production management, how the all the processes, main machine materials, methods, how you are going to manage effectively, efficiently. So that part is taken care under the production management. So here we'll go and concern with this manufacturing process. So manufacturing process, this refers to the science and technology, as you say, of manufacturing product effectively, efficiently, economically, and environment friendly. Through means what are the means by which you can achieve this manufacturing process effectively, efficiently, and economically, as well as environment friendly. The first option or that first point is always you have to keep in mind that application of existing manufacturing processes and system. So whatever the system you are having, whatever the process you wanted to involve during the production or production and manufacturing, that you have to use first. In the next step, what you will do, you are having the different sources, system, raw material, all these things. You need to select the proper materials, tools, machines, or whatever the system through which you wanted to go through and have your end product with you. After this, the next option you will have to go with, that is improvement of the existing material and processes. Once you recognize what kind of improvement you have to do, that with the system and out resources, input resources you are having with you, that you involve and improve the existing material and whatever the processes right now you are having to develop one product. So that development you can do by the existing materials and processes by its improvement. Next is a development of new material system. At last, if you are not having any new material, any new materials means what? The material you wanted to have for some specific purpose, like composite, ceramic, whatever it is, depending upon its application. But within your organization, in your system, you are not having. Let's develop it. through the various processes like star casting, whatever it is available in the market, or whatever the trends is going on to manufacture the composite materials that you can develop and use it. So the process and techniques, all such manufacturing process system technique have to be what? It should be technologically acceptable. Whatever the present technology, the next further after 10 years, it should be easily reproducible, and the process system and techniques should be easily adaptable. Next one is technically feasible. Whatever you are having, that should be technically feasible, means main, power, software, staff, those are easily adopt those technology to produce the products. Next one is economically viable, means you whatever for the pupil you are making, they should have such capability to use those products. And last, eco-friendly, it should not harmful to the environment. So next, classification of engineering manufacturing process, we may have nearly 6 to 7 in my PPT. In that, first one is primary shaping process. Shaping process means amorphous materials, those who are not having the shape, dimension and all. What you will do with the help of primary shaping process, you just give it to the shape or some rough dimensions after the shaping. Next one, secondary machining process. Secondary machining process means here generally we are going to concentrate, because ultimately our aim is to optimize the machining parameters in context of industry 4.0. So we'll deal with this, but right now here secondary machining process involves the removal of the material from the work pieces or raw material to get the desired shape and dimension, as well as also the quality of product in terms of surface finish, or in other term, there's a surface roughness values. Next one is metal forming processes. Here we use some pressure, some stress, some forces applied, but we are not going to remove the material in the form of unwanted material, or you can say in the form of chips. Without removing these chips, we are going to form or give some shape and dimensions to the raw materials to have the product. Next one is joining process. Joining process means two or more component you are going to join with the application of various joining processes which are available in the market. Next one, surface finishing operation, how you are going to have the good surface finish over your product. Maybe post processing you require to have to improve the quality of product in terms of surface finish. Then process affecting change in properties. This is related to your heat treatment, means after production what will happen if you require to alter the property depending upon your requirement. It should be ductile more, it should be having the tensile strength more along with the malleability. So such kind of improvement, maybe you some cases you require the surface to be harder than the core of the metal or product. So this kind of requirement can be fulfilled with the help of this heat treatment that could be done under a category of process affecting change in property. So if we'll go primary shaping process or manufacturing process of a product from an amorphous materials. So some processes produces finished product or articles into its usual form, whereas other do not and require further working to finish component to desired shape and dimensions. Means once you have given some shape or whatever the dimensions, that is not final for getting or delivering to the end users. Before that, you may have to go with some finishing processes or operations. So some of the important primary shaping process example is over here, casting. So next one is powder metallurgy. Next, plastic technology, gas cutting, bending, forging. These are the some of the methods through which you are going to give the shape to your raw material, which is in scattered form. Amorphous materials are there. Next, secondary or machining process. As I said, unwanted material form of workpiece you are having with you. Remove this unwanted material known as the chips. So the other name of this secondary manufacturing process, material removal process basically. So what it is doing, it is nothing but whatever the workpiece or job you are having or component you are having, you are going to produce required shape using the cutting tool. So though this cutting tool is always you are having the property harder than your workpiece material. So So this can be done by manual process or by using machine called machine tool. So by both way it is available traditional and non-traditional. Traditional generally have the direct contact with the workpiece and tool, and non-traditional having the non-direct contact. In between that you may have the interface medium, but there will be no direct contact in maximum cases. So some of the common secondary and manufacturing processes are turning, which is generally used to reduce the outer diameter of the cylindrical workpieces, and threading, cutting the threads on the surfaces or inside surfaces of the cylindrical tube, whatever you are having with you. Knurling, having you have to emboss the diamond shape pattern for the gripping purpose, like other milling operations, drilling, boring, planing, shaping, slottings. So these are the some of the name of the machining processes which generally means carried out using the different kind of machine tool. So some of them are maybe with the help of lathe, some of with the help of milling machine tool, drilling machine tool, shaper, milling. So all those machine tool generally involves removal of the material from the workpieces to have the desired shape and dimension. So next will come this metal forming processes. Metal forming process, as I said, there will be a application of pressure, forces, stress, or as a combination of any two of these. So that this pressure, force, or stresses are ultimately leading to give you change in the dimension of your raw material. So this change in the dimension you have to monitor in a such way that will give you the exact product which you wanted to have in terms of required shape and dimensions. Here maybe there will be maybe or sure there will be no such surface finish requirement is coming to the picture. But what will happen in maximum cases you have, or in all the cases you do not going to have the chips, the unwanted material which generally you have in case of material removal process. So there will be a two hot working process: forging, rolling, hot drying, extrusion, etc. Cold working process is that cold forging, cold rolling. So these are the some glimpse of the metal forming processes. So what is happening? Hot working, cold working, these two depends on the recrystallization temperature of your material. Above is hot working, below is cold working process. Joining processes you will have like welding, that brazing, soldering, riveting, screwing, press fitting, sintering, adhesive bonding, explosive welding, diffusion welding. So this joining process means what? You are having one assembled product. Assembled product means that is nothing but combination of various component which is giving you at last after assembly final product for working for a definite task. So let's consider an example. Like the ball pen consists of a body, refill, barrel, cap, and refill operating mechanism. All these parts are put together to form the product as a pen. Ceiling fan having the blades, motors, windings, all those. So after assembly, it may have to run over a certain speed and give you the air in terms of output. So similarly, you have to define this joining processing. Next one is surface finishing processes. So surface finishing processes are utilized for imparting intended surface finish on the surface of the job. So imparting a surface finish process means what will happen? Dimension of a part is not changed functionally. either a very negligible amount of material is removed from the certain material, or certain material is added to the surface of the job. Means there will be a negligible amount of material is going to be removed from the surface of the workpieces or your product. Either you have to apply some each and kind of agent to give the smoother surface, or that is ultimately going to give you the lesser surface roughness values. So some of the common use surface finishing processes are honing, lapping, super finishing, so polishing, crumbling. Organic finishes are there where you applied organic chemical to improve the surface. Sanding, deburring, electroplating is also available, buffing, metal spraying, painting. So all these are examples of your surface finishing processes. So processes affecting change in properties, as I told you, some heat treatment processes are going to be do. That is ultimately depend upon your requirement, what kind of the material you wanted to have with you, or what kind of product you wanted to have with you. Either improved tensile strength, either you can refer for the you should have the hard surfaces, soft core materials. So these are depending upon the your requirement, you provide some heat treatment processes. That is, those are known as the process affecting change in the property, or the processes for improving the property of your product. Next one, regenerating manufacturing. So this one is the recent one out of all. These are now in trendy fashion. So what is production of solid product in layer by layer? That is also known as the 3D printing, three-dimensional product you are going to develop or have at the end. So there will be various form of the raw material which you are going to utilize for generating a 3D object. So first form of material that you may have with you is liquid. So in the liquid form, that is considered in the process of stereolithography, where the resin are generally overlap, and with the application of heat, ultraviolet rays are going to generate the heat which is through the lens directed over the surfaces. That bonding will take place under the temperature and pressure. You will have one surfaces over there, you can cut through the laser and have the dimensions of your desired product. Next one, the powder form. If you are having the material in the powder form, that can be also done. So for this, selective laser sintering process is available as a 3D printer, 3D printing or regenerative process, where what is happening, the raw material in the powder form will spread on the table. There you apply some laser applications. So laser will tends to develop a heat. So this heat is ultimately going to give the binding between the powders. So what will happen after solidification? What you will have a end term or end product in the form of three-dimensional object. Next, wire. If you are having the material, raw material in the form of wire, for that, again, the FDM process is available as a regenerative manufacturing technology or process, in which what is happening, the wire form of raw material is fed layer by layer from top to bottom till the getting desired three-dimensional object at last. So these are the some of the example of regenerative process, how the material forms or various forms of material are utilized for generating the 3D objects or models. So out of the aforesaid group, regenerative manufacturing is the latest one, which is generally accomplished very rapidly and quite accurately using CAD CAM for rapid prototyping and tooling. So if we'll see machining operation and machine tools, just for a glimpse, what are the machining process in conventional form? You may have seen this from your graduation notes. So that those are the turning, drilling, milling. I already explained in previous slides. Again, we'll go through it and what are the machine tools those are available for doing this kind of machining operations or processes. So if you'll go the machining, as you know, there you will have the sharp cutting tool. This sharp cutting tool is going to cut the material which is generally harder than your workpiece material. Easily it will impart a force that will lead to go beyond the tensile strength of the your workpiece and leading to give ultimately unwanted material left in the form of chips due to these pressurized forces. So what is happening? Shape metal parts can be done geometric with the high precision and accuracy that can be achieved through the machining by using this sharp cutting tool. So generally what was happened forming process like casting, those are not that much precise or accurate in dimensions. So preliminary process like casting, once the product is passed from the casting or manufactured from the casting or primary process, that has to go through this secondary process just to have the precise and accurate product with you. So there is a one rotational here. What is happening along the one axis? It is having the axisymmetric where the from the surrounding the material is removed along its diameter or along its longitudinal length. Non-rotational prismatic part is also there that can be done with the help of drilling, milling. So generally pocket and slots are going to be have in your product or raw material. So here generating shapes. So this cylindrical shape is generally generated with the help of straight turning that you may have to rotate the cylindrical workpiece against the cutting edge of your tool that is going to remove the unwanted material in the form of chips. Similarly, if you want to conical shape, you have to turn again by feeding the cutting tool against the revolution of your workpiece, and in the form of cone you will have the end appearance of your raw material just because the in the taper turning move is somewhat moving at an angle, not in the straight line. If this movement is in the contour or some path it is going to follow, then you are have to say as a contour turning. Next one, plane milling and profile milling. Plane milling means what will happen, whatever the periphery of the milling cutter is going to have the contact with the entire surface of your this workpiece. It is ultimately removing the material, planing this material at a certain depth to reduce its thickness, maybe its width, whatever you are having in your plan to do it. Next, generated surfaces are generally through the profile miller, and with the help of profile, whatever the milling cutter you are having is a side milling cutter that you can use for the profiling. That is again removing the material from its surrounding. Forming to create shape that can be done with the help of form tool. With the help of drill bit or drilling machine, you can form a hole, maybe blind hole or through hole. And with the help of broach, one operation that is broaching machine is used to carry out, in which what will happen, this tool is known as the broach. So it has to pass through the your workpiece, and whatever the shape you have provided to your broach as a tool, that the same shape replicating in a your in the object. So what will happen? The shape of the broach is ultimately going to decide the shape and size of your broached workpieces. So in that, accordingly, it remove the material in broaching. Forming and generating again the thread cutting on lathe can be done. Slot milling, making the T slots, having the same shape of cutters. Along these, you have to remove the material. Before that, you have to give the passage for the spindle or whatever the extension you are having in your milling cutter to be attached, that has to be passed. Then only the T slot is going to become. So turning operation, if you will see the pictorial view is over here. Here what is happening? The titanium nitride coated carbide insert is used to remove the material from these workpieces. So these are material is known as the chips. This one is your workpiece. So here if you will see about the parameters which we are going to be optimized, what will be those parameters are depth of cut, that is nothing but insertion of your cutting edges inside the workpiece. Next one is the feed. Feed is what? In per revolution, the advancement of the cutting edge along the cutting length. Next one is the RPM, speed. Speed is nothing but whatever the RPM you have provided or whatever the rate at which it is revolving against the cutting edge. If you will say circumference speed, that will be given in terms of velocity pi dn by 1000 meter per minute. So again, generating surfaces, what are those? First one is facing, second one is taper turning when feed is inclined, then contour turning if the different path contour path it is going to move while removing the material, then form, then again alternate feet for the chamfering, then again for the parting off or cutting off, then for feed again it is one of the example of form cutting where the thread whatever you wanted to go have in cylindrical piece is replica of your cutting edges or the same profile you have to in incorporated in your cutting tool, then only the same profile of thread is going to be created on the cylindrical pieces. Then feed through which the boring is done inside this tube you are going to enlarge, then through the feed you can drill, through the knurling process you have the diamond shape for the gripping purpose. So this one is the machine tool, engine lathe, very well known to you all, having the various controls for the feed speed and whatever the depth of cut through the carriage, we always used to give. So simplest block diagram you can say or simplest pictorial view of your engine lathe. These are the some of the methods through which the workpiece is going to be held under motion. So there will be a three-jaw chuck, dog, collet, faceplate, ultimately going to function with your workpiece, which you are going to revolve against the cutting edge of the single point cutting tool. Multiple spindle bar machine will be there. One tool post where you can handle different kind of tools at a time. So here what is happening whenever you require to cut off, you can use one number of tool. Whenever you require to go for the straight turning, here you may have this turning tool, straight turning tool, with the help of which you can perform straight turning. Then in third number you may have the form tool. So these are the attached tool 1, 2, 3, 4, 5, 6 on one common tool post. That is also known as in some cases turret. Next one, horizontal boring is there. So boring bar made of cemented carbide and indexable cement carbide inserts are here. If you will go revolve the tube or cylindrical pieces inside that, it is having the hole and you wanted to enlarge, you can easily. So in both the cases, feed motion is provided with the help of this tool trowel or tool post trowel. So, and in another case, the table is uh, going to move or the feed motion is provided to your table. Operation related to drilling are this one. So drilling operation, the machining parameter may be RPM, the cone angle, point angle, the force, the torque. These are the some of the parameter which you need to monitor or you need to optimize for the good responses. That we'll discuss how and where, how you can monitor. So one is through hole, blind hole. These are the operations you can do. Next one, two form of milling. If you are having the milling machine tool with the help of these two cutter, one is the peripheral and another one is the face one. So what is happening here? You are going to provide the feed against the rotation of your cutter, milling cutter. It is removing the material. All these are the secondary process. So ultimately you are going to remove the material from the workpieces. So here the face milling cases. So if it is covering the entire slab, slotting, if you are wanted to cut the slot, the size and shape of the cutter should be such that it has to be give the narrow path on the your workpiece after cutting. Then side milling, side of the workpiece having the cutting edges on its side, straddle milling on both the side, it is going to be cut simultaneously. Next, milling, this up milling and down milling concept is will be always there. Towards the feed motion, if you are moving the, or you can say, if your cutter is moving in clockwise direction, and along the same direction, if you are moving your workpiece, that is the case of your down milling. If the rotation against the rotation, if you are feeding your workpiece, that is your up milling case. That is conventionally used initial stage. So conventional face milling is there. Here is the pictorial view of high speed face milling using indexable inserts. Next one, through the milling, we can generate these many shapes on the workpiece: end milling, profile milling, pocket milling, surface contouring. So what is happening while creating these surfaces or removing the material from the surfaces of the workpiece? Ultimately, we need to monitor the parameters, not only in the case of conventional, but also in the case of non-conventional. So those variables, parameters, and factors are monitored properly for getting the desired output responses. So for those parameters, we need to go for the optimization techniques, technology, or processes. We'll discuss this. So milling machines look like this, like horizontal knee and column milling machine, vertical knee and column milling machine, just depending upon its ram situations or saddles situations. Or you can say the spindle on which the cutter is going to be mounted. One is the vertical one is the horizontal one. Then machining center maybe comprises having the lathe machine, then a milling machine, drilling machine, or you may have the separate section in where you are having all kind of lathe, turret lathe, CNC lathe, woodworking, whatever it is. So those are you can term as a machining center. But nowadays these are the some example as highly automated machine tool. You can keep at one center. That will become one machining center. Then CNC control machine tools are available. Minimal human intervention is required only. Next, automatic tool changing, pallet shuttle, automatic work part positioning. These are some of the characteristics which are generally available in one machining centers. So most of the machine tools are now CNC machines, computerically, computer numerically operated. So broaching, as I earlier told, you will have the broach tool which is going to remove the material, but ultimately this removal of the material is dependent upon the whatever the shape and sizes you wanted to have in your end product. So this one when we do generally we need to make some external broaching for the we need to make some slots outside the workpiece or outside the product. Then we go for the external broaching where the external thread will be there, and internal broaching also whenever you need to have the some slots hole I slot, T slot, some shape, square, rectangle, whatever it is. So depending on your requirement, you can prefer external and internal broaching processes. These are the sawing for cutting of the materials. So turning involved turret lathes, checking machine, bar machines, automated screw machines. So all these, what is happening, slight deviation you may have. In one case, you may have no tail stroke. In one case, you are having the turret where you are holding the multiple tool. So whenever required, you can engage a definite tool for a certain operations, which can be performed only with the help of that definite tool. So vertical boring mill, these are all again example of one machine tool. Drilling. So as I said, that round hole as a work part. Boring can enlarge an existing hole. Cutting tool called as a drill or drill bit. Machine tool is nothing but your drill press. So here with the help of drilling you can create hole in large hole, as well as whenever required you can make a countersink or a counterpart at the top of the surfaces to hold your nut bolts and all. So further, if you will see in milling again, if you are having the side view for the slab milling, how it enters and how it leaves, relieve the work. So that can be easily understand with the help of this picture, where the cutter position at the end is this, and whenever the center of this cutter is going to be passed, at that point of time the cutting of material is over. But in case of cutter entry, whenever the center is away, it started cutting. That is known as the approach length, and actual length of machining will be this. Similarly, in case of face milling, you will have the overrun or over travel and as well as approach travel. So here what is happening, till the center reaches at the end of over travel length, it has to perform the cutting, and it has to be start the cutting when the first teeth is going to, or circumference is going to be come in contact with the your workpieces. Same as in case of face milling, but here what is happening, the same you may have up overrun and approach length for cutting off some width of the material. So again, when you are going to be start touching its circumference, it has to remove the material and till the end point which is going away from the workpiece. So high speed machining will be there. Also there you need to monitor the parameter, optimize the parameters. What are those? In case of this aluminum, if 600 plus, it is conventional speed. But if you are going 3600 plus meter per minute, that will be treated as a high speed. This has been taken as a reference from the canometer industries. So this one is the, this Canametal is the good supplier of the cutting inserts, tools and all, as well as the, it is, this Canametal also used to publish the handbook related to your thumb rule or whatever the, depending upon the material, depending upon the required cut, what should be the speed, feed, depth of cut, for the nature of the material, that you can select with the help of this Canametal handbook. So high speed machining means what? The high production rate you are going to achieve. Shorten lead time will be there. Rapid transfer speed, high feed rate will be there, and automatic tool changes may be there to just carry out the machining operations or the removal processes as fast as possible. We had to concentrate on these 4 points. So these are only achieved when you are having the high RPM bearing that can be withstand with the high speed. Advanced CNC motion control, you require balance cutting tool to minimize the vibration, that has to be there, because you are going to run the machine with a high speed, so coolant delivery system should be there due to the pressure or high pressure, or maybe there is a generation of temperature due to high pressure and temperature. You require this coolant delivery system, chip control and removal system should be there because you are running the machines in very high speeds. So again, these are the same. So let's have an example. As showing in figure A, you are having objective to cut the cylindrical workpieces, and at last you have the material in this form as a final product to deliver in the next section. So for this, how you can execute your plan? First, you will go for the turning. Then next, for the milling to have this surface. Then next, drilling to have the hole over here. Then parting off or cutting off tool to just separate this piece or this dimension, whatever you provide. After that, you need to separate it from the raw material, maybe having the larger length as shown in A. So that we need to cut. So the turn, mill and drill all have been performed sequentially. So sequence of operation on mill turn center is required to have the final shape of this. So during machining or getting the desired shape by each operation, we monitored some parameters. So those parameters need to be optimized. How we'll see. Next, shaping and planing, another machine tools. So these machine tools are generally used to make the slots on the workpieces. So in one cases, you have to move the cutting tool against the stationary workpieces. In other case planing, you may have to move the workpieces which is fixed on the table, workpiece table against the stationary cutting tool. But this cutting tool has to be moved also in each every pass, same as like in shaper. So with the help of this shaper or planer, we generally manufacture these grooves, square grooves, V grooves, T slots, diagonal slots, gear teeth can be also cut. Again, drilling machine pictorial view is over here. So selection criteria of manufacturing process generally depends upon the rate of production, how much productivity you want. Then next one is the cost. The cost should be effective, or you have to involve such set of sequences that will lead to give you the lower cost of product and minimum wastage of material. Next one is the performance, how effectively and efficiently you are doing the processes to getting the end product. Size, then shape. What is the size of your work pieces and what kind of shape you are required. So these are the some of the criteria, not only here in conventional, in non-conventional also you need to identify, or you need to have all these criteria in your mind while choosing some processes or machine tool under which you are going to carry out the processes. So non-conventional and non-traditional machining, let's have a glimpse of this or brief about this also. So first one you can categorize as a mechanical machining. Mechanical machining means first one, let's consider ultrasonic machine and water jet machining. So here what is happening, the solid grains suspended in abrasive slurry is going to erode the material from the workpieces. So whatever the erosion is going to be take place with the abrasive slurries or through the impact of water jet, that is also at high pressure, is going to remove or erode the material from the workpieces. So these are some of the mechanical machining where actually the abrasive slurries and water jet are going to use for eroding the material to have a definite shape and size after removal of the material in the form of minute chips. So here in case of ultrasonic machining, abrasion is going to happen. Here in water jet machining case, the cutting is going to happen with the high pressure jet of the water. So here the medium between this workpiece or this abrasive slurries, here will be the jet having of the fluid. So fluid jet is going to be strike on the workpiece. Here slurry is going to make contact with the workpiece. So whatever the tool, again it should be replica of your slots or whatever you wanted to cut against the same replica you are going to have. But in water jet machining, you have to strike it off, erode it, and have the end dimension. Next, after mechanical thermal machining. So thermal machining means instead of mechanical energy, now you are going to use the thermal energy. So here what is happening, if you will consider the case of EDM, the discharge will be there, which is electric discharge. So what is happening, this discharge is nothing but going to have a plasma environment ionized media through which the spark is going to be generated and strike on the workpiece. The medium in between this, you will have the dielectric. Same as in electron beam machine under the vacuum condition, high velocity electron or high energy electron is going to be impact and remove the material. Next, in case of laser beam machining, the photon or laser is going to be impact. Maybe it is directed through the various lenses, how it is going towards the workpiece and strike on a particular spot, remove the material. So in all these cases, what we are doing, we are generally melting and vaporizing the workpiece material from a particular spot. So many secondary phenomena occur during machining, micro cracking, formation of heat affected zone, and striation, etc. After what's this? Next one, the source of heat could be plasma as during EDM and PBM, or photon as during LBM, electron in EBM, ion in IBM. So these are the some of the non-conventional machining example of thermal machining time. So again here we have to somewhere see about the current, pulse on, pulse off time, the electron beam intensity, nozzle shape, standoff distance, all those we have to monitor to get the desired responses in terms of your surface finish, forces, whatever you have to get at the end to assess your product. So if you'll see, another one is chemical and electrochemical machining is also there, where the chemical etching is going to happen. So in one case through the electrolyte medium, and another case etchant is going to be used. So here what is happening, photochemical blanking all use a chemical dissolution action to remove the machining alloyance through ion in etchant. Electrochemical machining uses the electrochemical dissolution phase to remove the machining alloyance using ion transfer in an electrolytic cell. So here you can see water jet machining, the pictorial view. You may have some standoff distance, nozzle shape, angles, materials of this nozzle. Those can be treated as a parameter or variable which may be further needed to be optimized to get the good performance of your this operation or processes. So here 0.8 is standoff distance. This one is the internal diameters through which the this jet is going to be passed. In case of abrasive, it is abrasives. So ultrasonic machining will be also there with you in machining center. There what is happening? The ultrasonic frequency that is going to be just have contact with abrasive slurry, which is going to erode the workpieces from the material from these workpieces. So whatever the abrasive slurry is going to perform actual cutting, which is pumped inside near the zone or in between the horn and workpiece to remove the material. So whatever the abrasive slurry is actually going to give you the shape, same as shape you are having in your horn as a tool. So there will be many mechanical arrangement will be there to ultimately assist you to or to accomplish the removal of the process through the ultrasonic principle. Here we are having the ADM setup. How it works is like this. So ionization, whatever the dielectric fluid you are having inside that, you do your workpiece says this one is the your electrode. So whatever the spark is going to be generated in between, this spark is ultimately going to remove the material. So in the form of erosion, evaporation. Next one is electron beam machining. You can see the high beam is going to be directed to the various lenses to strike the workpieces. Means the kinetic energy or high heat is ultimately going to evaporate the materials in the form of chip from the workpiece. So this one is the laser beam machining setup. How it works? The flashlight or laser is there, which is from the flash lamp, both the sides, and this light is going to be directed through the lens. Focal length will be there, some intensity will be there, some material for this will be there, which you have to be monitor or optimize for the correct performance. Same plasma arc machining will be also available. So again, as I said, in case of traditional machining, you have to see some criteria how you are going to carry on depending upon its production rate, cost, performance, size, and shape. The same is applied for the non-conventional machining also. So after this, let's come to this Industrial Revolution 4.0. We are having the human civilization from the ancient time to this time. So somewhere we were using the traditional machining, then came across with the non-conventional machining, non-traditional machining. Somewhere in the initial stage, they were using the mechanized kind of instrument, tools, and all. Then after some era, some evolution happened. The next generation having some more advanced component with you, more advanced devices with you that are day or by era added up, and some revolution happen in manufacturing industry. So industrial revolution 4.0, how it's going from one phase to next phase. If you'll see, the first industrial revolution came when the water and steam power is invented. Water and steam power were utilized. Or in this time, what will happen? Whatever the maneuver or manually the work were carried out by the operators or by the workers for making any kind of product, this manual interface are going. This manual interface were just replaced by this water and steam power. Whatever power you are providing to the manually is replaced by this water and steam power. So first mechanical loom were invented in 1784 as a revolution. Next, second industrial revolution came when there is a development in some sector, like electrical energy is going to come into the picture to drive the your various mechanical component. There they use the conveyor belt. They have segregated the operators depending upon their work throughput. So what was happen in second industrial revolution, the mass production they started by using this conveyor belt and electrical energy. And in the third industrial revolution, that is basically come into the picture when the IT and electronic sector came across to how these are going to be operated, or complete automation is started. So what was happening once the human intervention is started at the initial stage, then after some time it is going to reduce the human intervention for the processes to be carried out for the manufacturing any product. So here what is happening, the automation they started doing. One of the major role is played by the PLC, programmable logic controller. So this is under the third industrial revolution. Then fourth industrial revolution came, in that based on the use of cyber physical system. Here what was happen, the internet and whatever the components as physical component you were having, those are having connection with the internet. So with the help of the internet, now you are going to control whatever the automated part that has been developed in third industrial revolution, that can be easily controlled with the application of this internet of things. So here in this fourth industrial revolution, what was happened, this cloud computing came into the picture, big data, artificial intelligence and all. So everything is now available in the cloud. You can access the data, you can draw some conclusion, as well as in this big data, large number of data is stored that can be analyzed whenever you require. You can have it and draw some conclusion. So the data storage capacity that has now grown up with the help of these new technologies, that these new technologies which came up in the era of this fourth industrial revolution. But if you will see the degree of complexity that is also increased with each industrial revolution. So the fourth industrial revolution is leading the intelligent information society and the digital transformation and its advanced technologies. So artificial intelligence, this one also came into the picture, where what will happen? Now you are making the machines to learn by themselves and react according to the situation as per the requirement. So starting from the first revolution to the till fourth industrial revolution, what was happening? The some form of energy is going to be used, some automation that done. After automation, some accessibility was means exploit, or you can say the more accessible of the systems or whatever the manufacturing system we are having, that is more accessible to the operators. From one place you can sit and operate the machines that are situated in different place. So that can be now possible in fourth industrial revolution. Once you are going to enter a part design and give the command from here itself, that you can monitor now with the help of your display or monitor, and see the progress of your component, how it is going to be manufactured, and at last what the product appearance is having at the end with you during the process, after the process, and on the process. So what are the main pillars of Industry 4.0? So this building block of Industry 4.0 is shown over here, that is cloud computing. So data are now going to be stored, the large amount of data you are having to be accessed, analyze, and do draw some conclusion. So big data analytics is there. So storage system you are having. Next, augmented reality is there, where you can see where you are having your object and with the interfaces with your real world, virtual world, that is virtual reality. Next one, adaptive manufacture is. Then cyber security is also needed, because all the things are going to be handled to the cloud, big data, all those are easily operated with the help of internet. So cyber attack and cyber security is one of the pillar which is going to support the industry 4.0. Then internet of things, everything is going to be controlled with the help of internet. So Next one is system integration is required, simulation is required, and main thing, robotic automation or automation robots is required to actually perform the operation on the designated places or machining centers. So as for the technology, robotics deal with the design, construction, operation, and it's replacing human on assembly line for making the component. 3D printing is any of various process in which material is joined, as we have seen, solidify under the computer control to create three-dimensional object, the manufacturing customized component. So whatever the customized component you can now build with the help of 3D printer. Next, big data. As I said, that huge number of data you may collect, perform whatever the uses to refer to the data sets that are too large or complex for a traditional data processing application, analytics. So understanding collected data, these are some of the functions that you can have to perform with the huge number of data, which is known as big data. Next one, respective to pupil, increased efficiency, reduction in labor per unit, skill development, upskill, reskilling that is required in continuously, mindset change, only to handle disruption, monitor and corrective action. These are the time where you actually require the pupil for handling during the disruption and monitoring correct. These are the some means initial disruption if you want, or at last disruption you want. There you can have the pupil intervention and monitoring for the monitoring and as well as for the correction you may require this human being. Otherwise all the things are going to be automated. Next, constant communication through the process, data exchange between the component, decentralized and decision making, any process where the decision making authority is distributed throughout a large group. So standardization, easy of customization. These are the some of the benefits in the terms of processes, people, and technology, which is nothing but going to help to have your product, which is you are going to supply to the end user. So what are those technological benefit, people benefit, and process benefit due to the application of this industry 4.0 is over here. Next one, social changes due to fourth industrial revolution we have seen are intellectualization, human machine. Means here what is happening, the transformation of knowledge or the movement of knowledge from the human being to the machine. Now you are making the machine more intelligent through the various technology. So here what is happening, you are transforming or giving one intelligent society which is going to build you a human machine interaction or relationship, which is nothing but it is in terms of machine learning, deep learning, big data, all these are going to just train one artificial human which is going to be operated in place of human being. So one human is going to teach the machine, machine is going to be operated and deal with the situations. Changes in recognition of human identity, job topography are commonplace. Virtualization, reality virtual, acceleration of the fusion of virtual and reality. So here what is happening, the new products, VR, AR, smart cars, telemedicine, virtual labs came into the picture. So like social economic activities, those are the some of the impact on the society you may see. Human experience and cognitive domain become blurred. New services in various field of industry can be created. So hyperconnection, human things, transformation into hyperconnection society can also be observed easily. These are the some of the changes in the society we can see. So hyperconnection causes new group behavior pattern. So human things interaction, or you can say internet of everything is now coming into the picture, which is creating a separate society kind of things. These are the some of the changes we have seen through this fourth industrial revolutions, where what is happening now, not only you are interacting with the human being, but interacting with the machine kind of thing, non-living things, and after interacting with them, interacting with those machines, what is happening? You are making those machines intelligent to interact with you and communicate with you, and this is ultimately leading to give you the separate society kind of pattern, society behavior pattern and all. So conventional industrial production and the industry 4.0. Conventionally, what we look for in the previous era or previous stages of this production industry, we generally look upon production planning and control, IT supports, like ERP, MEP manufacturing execution system, which is generally for the tracking and tracing of the your processes, object, what is the stages like that. Then data management. But these are replaced in Industry 4.0 in terms of cyber physical system and IoT, where the physically you are going to be have the connection and interact with the help of this internet. And in this IT support, ERP MES is now converted in the form of smart factory, maybe smart manufacturing, smart foundry, smart machining. This kind of setup you are having with you now in under the Industry 4.0. So big data, cloud, and cyber security. This has taken the place of your data management, where what will happen? Large, huge number of data is going to be stored, transfer, analyze, and after analyzing, you are coming up with the some conclusion. Now you are not restricted to have the limited number of data. You are having a vast number of data through which you can come your fruitful conclusion through which you can carry out your processes. So advanced manufacturing system generally implies that sensors, which is generally used for tracing and predictability, for predicting where it is actually in soft floor, where actually the particular product is placed while going under the certain sequence of operation that you can track with the help of sensors. Then 3D printing, scrap elimination, customization of the product is easily done with the help of 3D printing. Next, cloud computing, again, big data and cyber security is there, having the major role. Robotics is having the role for the autonomy and productivity. So productivity is obviously going to be increased when the human being are replaced by the robots, and autonomy will be there. Maybe you are having the more accuracy in your dimensions and all, and surface accuracy in your dimension, surface finish, all this you may be having in the improved form when you are applying this robotics in place of humankind. So three clusters merging in cyber physical system driven by AI and robots, that is those are physical, biological, and digital. So you can see easily what are the physical entities you are having with you, what are the biological advancement you can have with the help of this, and the digital things you are having with you, that is ultimately going to give you the at the end the output in terms of product that is defining you the goods quality, as well as whatever the service says you are providing for the mains material welfare. In that direction it is contributed well. So these three cluster merging is always involved in future or in the present. So what are the benefits of the moving on to the industry 4.0? So that is increased flexibility, productivity, efficiency, quality, reduce time into market, more R&D activities, and development of new skills. Obviously, if you are having the large number of accessibility to the data, large number of accessibility to the technology, large ICT, vast ICT you are having, that ultimately leading to give you this much benefits, which will nothing but uh, have the parallel operations, shorter time frames, work with existing infrastructure will be easily can be done. Then fail fast and learn fast, then low cost. These are going to be achieved with the help of this Industry 4.0 application in your manufacturing industry. So Internet of Things means you are going to connect it all the physical system through the internet. Not only this one is going to be having connection with the your industry, but also it may have the interfaces with each other. These interfaces through the internet is going to track your component at any stage, and at the time of completion you may have the alarm your product is completed, now ready for the shipment. Not only that point of time, it is also now considered for the supply chain management, supply chain 4.0. There they have some digital information, or digitalization is going to be done, or it is already happened. So what will happen in the value chain, it is also improvised. So Internet of everything, you may see the smart grid, smart buildings, smart home, social web, all are going to be connected with each other. So these are done through the various means also, like Microsoft. So we are having the connection in any ways for anything, that is your Internet of anything. These are cyber security and cyber attacks, some data country wise. So that is the one of the pillars, or we have to think about it, how to improve the security and how you can safeguard your organization, which is under the application of your industry 4.2 to safeguard from the cyber attack. So information, communication, and technology makes this difference. What are these difference? Laser-based manufacturing now able to manufacture any kind of, any shape, any dimensions. Simulation can be done. Whatever the cyber physical system for process chain optimization can be done. Okay. So robotics is going to be employed for manufacturing the components. So whatever happening, the automation is done, human is going to be replaced, modeling and simulation is happening. So CAD, KE, CAP, CAM, DMU, and virtual reality, augmented reality, all those kind of technology is going to be used. So what is happening, that is complete information is going to pass from one section to another section, that is under the your information and communication technology. So being developed or new on the market, or maybe this one is already developed. What are those things? Robotics for weather forecasting. You may send these in anywhere from where, through the help of sensors. It can collect the information, store in the big data, analyze it, and give your conclusion what is going to be happen, or what is actually happening. So virtual reality, artificial intelligence is there, where you can teach the machines, make this artificial thing intelligent, maybe comparable or very close to your human being intelligence. So virtual reality is there. Whatever you are having through the one headset, you can come to know virtually how you can see the actuality. So what is going to be happen if these things I will change from here, this particular place to that particular place? Like kind of analysis can be done. 3D printer is there for the three-dimensional product printing. Google smart watches, self-driving car. So these are the new on the market, or maybe already developed. People are going ahead from this also. So virtual reality, augmented reality in classrooms. So AR will soon affect the conventional learning process and could grant student extra detailed information about any subject and make complex information easier to understand. So AR animated content in classroom lessons should catch students' attention in dynamic day and age. So VR is virtual reality is manufacturing what is happening, the structure, optimize the location, flow of production line, position automation line. This can be easily controlled through the VR. So these are the some data expectation from the industry 4.0 by various reasons. Fourth industrial revolution cross country, how these are the data. This one is the old one. So artificial intelligence is the future of economic growth. What percentage they have grown. So that is easily understandable how it importance or how the industry 4.0 is important in the manufacturing organization. If you see the university perspective, there you will have the change of organizational structure, how in terms of change of business model, the next cooperative structure enhancing indisciplinary, new concept of faculties or departments. So likewise, change of accreditation process in everywhere you can involve. So what will happen? Your process is going to be smoother, faster, and somehow you can say reliable to cope up with the new market demands. So let's come to the actual this optimization, how we generally use to carry out for the conventional and non-conventional machining process. So in industry 4.0, what is happening, what we are going to be carry out to applying various technology, and those technology is going to be monitored the parameters which are actually involved in the shop floor. Initially it was performed by the humankind. Now let us it is going to be performed by the some automated robot or some machines manipulators and all. But whatever the performance or processes are carrying out, that is ultimately going to give you the end. Whatever the processes carried out through the advanced technology, that is need to be optimized through the various optimization processes. So here the optimization means what? You may have the some objective. So objective means there will be some problem that you have to formulate. So that after formulation of the problem, you need to see what are the inputs, what are the outputs, how you are going to have the optimum value of your input, which is going to give you the exact desired uh, output or responses at the end. So this optimum thing is not only to maximize the variables value, but also in some cases minimize, and or in some cases both you have to do. For the some parameter need to be maximized, some parameter need to be minimized to get the desired responses. So formulation of design problem is a mathematical programming problem necessary. So these are the some of the objectives. So at last, if you'll see, define the global optimum in comparison to the relative or local optimum, how you are close to your response. So introduction preliminary requires for the basic optimization problem is, or basic component of an optimization problem consists an objective function expresses the main aim of the model, which is either to be minimized or maximized. Next thing, you may have this set of unknown that is known as the variable. So which ultimately you are going to control to monitor your objective function, or through the objective function you are having to get something, some values that has to be monitored with the help of changing these variables values. Definitely there you will have the some constraint. Beyond this you cannot vary one variable. Some variable may have some limitation, like minimum value you should keep this much, maximum value you should keep this much. Maybe due to the power constraint, maybe due to the configuration of your machines constraint. So these are the some of the restriction or constraint you are always having with you, and that need to be imposed with the objective functions. So many optimization problem have a single objective function. The two intersecting exceptions are no objective functions means what? User does not particularly want to optimize anything. So there is a no reason to define an objective function, usually called a feasibility problem. So multiple objective function in the practice problem with multiple objective are reformed as single objective problem by either forming or giving the weightage to the each combination, and different objective or by treating some of the objective by constraint. So in one cases you may have the single objective, in other cases you may have the multiple objective. This multiple objective you may convert by providing the weights into the single objective. So what will happen? Ultimately at last you may have to come up with a single objective which will going to satisfy the multiple purpose. So that can how you are going to convert in a single objective by providing the some weight to the your input variable or output variables, and at last to the analysis you may come to the final conclusion. So statement of optimization problem, how you generally write like this: to find x, that is the variable having some constraint, it should not be max, or it should not be more than this value, it should not be less than this value, like this. So constraint and objective function always you have to be defined. Then in the next stage what will happen? What will happen? What will happen? X in a n-dimensional vector called the design vector, fx is called the objective functions. So fx is called the objective function, gx, L, jx are the inequality and equality constraint respectively. This type of problem is called the constraint optimization problem. So optimization problem can be defined without any constraint as well as unconstrained optimization problems. So these are the, if you'll see, the fx is some objective function and c is the constant under considerations. So it can form a family of surfaces in the design space called the objective function space. This C constraint, the surfaces. So what will happen if you want to see the maximum? This will be the optimum point, which is nothing but these are the feasible region, or with the help of this you can easily understand whatever the function surfaces you have generated with the help of this constraint, along with this constraint, and having the some feasible solution region out of which where the maximum point is going to be have along the surfaces will be your optimum point if your case is for the maximization. So variable and constraints, there will be variables. If there is a no variable, we cannot define the objective function and the problem constraint. Constraints should be always imposed on the variable. Then constraint can be broadly classified behavioral, functional constraint, geometrical or site constraint, depending upon its situation. Next, constraint surfaces, same as C1, C2, C3, 4. You drawn, and the where it is touches the feasible region point, you got the maximum that can be treated as a minimum point. So here you can see behavioral constraint you are having in feasible region, feasible region. So in case of maximum, you may have the points here, and the local minima you are having here, global minima you will have somewhere within this region. So optimization machining parameter is crucial for improving the productivity, reducing cost, and enhancing surface quality. So various, it's time is over. Okay, so let
Yeah,
me
time
skip.
completed.
So here,
Sorry.
if you so actually we now actually we have this uh, what I wanted to say that now actually I entered in the optimization processes. So let me have at least glimpse so the audience may come to know what are the optimization techniques are utilized nowadays for the finding out the optimum level of parameters related to your machining processes. So optimizing machining parameter means improving productivity, reducing cost, and enhancing the surface quality. If these are the your aim, respective to your this aim, you may have the various traditional optimization methods like Toguchi one, response surface methodology, design of experiment is there, regression analysis, analytical and numerical methods are there. So meta-heuristics optimization methods are also available nowadays. It is widely utilized by various researchers, genetic algorithm, particle swarm optimization, and so these are the some methods which are widely used in the past days. Now the days came where the hybrid optimization methods are being utilized. So here what is happening, the benefits of two method is going to be combined, and that two method combination is treated as a hybrid or called as a hybridization of optimization method, which is leading to give you the better result. Why? Because this is having the benefits of two methodology or two optimization techniques. The choice of optimization method depends upon these. Next example with MMC, if you see, you have considered one turning operation, cost through the cause and effect diagram, you are having some parameters to be monitored. How that parameter is going to be optimized to the hybridization. Let me go to the see, if you perform a turning operation, you are having some parameters values available with you, which you can treat as a constraint. This much value I cannot vary beyond this, like that. So after performance, you may have some responses, cutting force, surface roughness, specific power, and all this. So those responses is going to have the indicator where you are getting the optimum values of your parameter or not. Of through the optimum value of your machining parameters, you are getting the desired value of surface roughness, cutting force, and specific power. These are the some data. So this data I have taken in my slides to just explain the various optimization technology which are of hybrid kind to get the optimum results for your machining parameters. So here what is happening, the PCA is going to be coupled with GRA in first case. Then next PCA is going to couple with GRA which is combined with RSM. Then particle swarm optimization technique is coupled with PCA coupled GRA. Then also the ANN is also going to couple with multi-objective GA. So the hybridization is done with GA, RSM, GRA and ANN. So ultimately how it works is like this. So initially you have to conduct the experiment, you got the data points, then perform some calculations, and whenever required you have to merge it, feed into the GA. The toolbox will give you the iteration epochs which will corresponding to the minimum or whatever the fitness value you are getting, corresponding to which you may have the optimum value of your parameters. So some calculation tables, fitness function which you are going to be imposed, through which the fitness value where you are having the minimum corresponding to this, the variables V, F, and D, that is cutting variable, is going to show you some value that you may consider for the optimal value and go for the confirmatory test. So this is GA couple GRA. Then next one is the GRA plus RSM. Then next RSM is giving some control plot for verifying the results, and confirmatory test to confirming the results. Next, PSO with GRA is also particle swarm analysis or particle swarm optimization technique can be also coupled with the GA to give the optimum result of machining parameter that has been already confirmed through the confirmatory experiment. So NN plus GRA that you can also couple. This one is the flow diagram, how it is going to be executed. So all this MQL condition is for the machining one. So this one is some flow, how you can couple two methods and two, or I should say, how you can hybridize the optimization technology. Okay, thank you.
Thank you, Dr. Umesh sir, for your valuable lecture. Sir, given the insight of this lecture and given lot of information regarding this lecture. So I request you, any participants have any queries, please ask the question to Dr. Umesh sir. Anyone, any
Sir, I have
questions?
one question. Sir, first I request to please share the slide. It's a very informative session.
What question?
Sir, I first requesting to please share this slide. My question is regarding you have shown that there is a no objective function optimization.
Yes, yes.
Will you share some examples with examples?
No objective function optimization. So
Yeah.
what is happening when you are going to consider some responses, say like surface roughness. So what is happening? The industry is going to ask you this much surface roughness I wanted to have. But inbuilt in your machining, through the machining, you are getting in that range of surface roughness. Then what you will do without carrying out any optimization process, objective function and all, you just turn it out, you have the output in whatever the company or industry asked you, the same you can supply. So indirectly you are having the objective function through the company to give the such reference value product or such value of surface finish on the product to be supplied. But there is no need of carrying out the optimization through the objective, because already you are having some setup of such kind of setup which is going to give you the same responses which the industry asked for you.
Thank you, sir. Sir, once again, I request please share the slide to us because it is
Okay.
very informative slide sessions.
Okay, thank you.
So thank you,
Good
sir.
evening, sir.
Yes.
Sir, in this particular optimization various techniques, how we can relate this optimization with any machine learning model, and how much research further available in this particular area?
This, if you will see the optimization methodology or technique which you are going to be used, so any kind of machine learning behind that, some code is running, some mathematical formulation is there. So this mathematical formulation or whatever the code that you are going to impose in machine, or you are going to teach your machine, these are ultimately having implication of your these optimizations. Means, let's suppose you wanted to have one machine learning program which will give you certain range of input or output. So behind that, some set of instruction is running in the form of codes. So by this way, the research is carrying out,
Okay, sir.
respective to
Thank you.
optimization.
Thank you, sir.
Okay, I requested all participants because of time limitation. Our next speaker is waiting. On the behalf of Aditya University, I really thanks to our speaker, Dr. Umesh Khande.
Okay.
The next speaker, Dr. Pritam Kumar Das will give the introduction, brief introduction about the next speaker.
Thank you. Thank you, sir.
Thank you, Dr. Umesh.
Thank you. Shall I leave?
Yeah, sir, you can leave, sir. Thank you for your presentation. Good evening to all the participants. Myself, Dr. Preetham, and it is an absolute honor to introduce our esteemed speaker, Dr. Jitendra Kumar Chaurasia, a distinguished expert in the field of metal additive manufacturing. Dr. Chaurasia is currently serving as the Senior Manager, Metal AM System Design and Architecture at Liaison Engineers Private Limited, Chennai, Tamil Nadu. With over 8 years of experience in directed energy deposition processes, he is actively involved in research and development to build large format metal 3D printers. His expertise spans experimental characterization, mathematical modeling, real-time processes monitoring, closed loop controlling, data acquisition, and visualization techniques. Dr. Chaurasia holds a PhD in metal additive manufacturing from the NIT Karnataka. His numerical methods based on finite element and finite volume methods have made significant contributions to understanding thermomechanical and thermofluid behavior in laser processing. Its outstanding contributions have earned him prestigious awards, including the Special Achievers Award from VIT Vellore, Best Researcher Award in Dead Application from the Additive Manufacturing Society of India, and Best PhD Thesis Award from the 3D Graphy. With 10 plus international journal publications, 12 plus international conference proceedings, and multiple book chapters, he's a highly regarded researcher collaborating with central government agencies and R&D organizations. We are really privileged to have him with us today, and we are eagerly looking forward to his insights and expertise. Please, all of you join with me to welcoming the Dr. Jitendra Kumar Chaurasia, sir. Now the session is with you. Please continue, sir.
Hello, good evening, sir.
Yeah, good evening. So good to see there are almost 68 people here at this time. Looks like people are really interested to learn something. So it becomes more responsibility on me to, make use of this time and get started. So I'll share my screen. I hope my screen is visible.
Yes, sir. Yes, sir. Yeah, very much well.
All right. So let me take it to full screen. Okay. So good evening once again, everybody. Thanks for the introduction and thanks for inviting me for this FDP. And it's a real pleasure to, introduce by myself and what I do at Liaison Engineers Private Limited. Just to be, more practical, my presentation is going to be slightly towards achievable things, right? Not much theoretical, and I'll try to make it interesting as we go. So as we move, let me just give you a quick agenda what we're going to discuss. So first of all, I'll introduce you about Metal AM. I'll just go quickly, real quick here, just to give you key insight because there will be several speakers. I checked the agenda and some people have already talked about it. Then I'll just make you understand the key concept, what is simulation and what is digital twin, role of simulation, digital twin in additive manufacturing, and then future. So that brings to the first point that is called the additive manufacturing, and everybody is talking about it. Everybody. If you are lucky enough, especially Metal AM, I think this is the best skill at this moment in India. I would say there are a lot of companies evolving. They need people with expertise. In fact, I need. So someone interesting, get my email ID from the organizer. So currently, just to give you a background, we are making laser DED based system, big machines like building parts which are more than 2 meters, 3 times of my height. So that is what I'm doing right now. So I'm heading a project where we are developing. And why I feel this topic is very relevant to me because when we are building this machine, I'm leading a team which is developing software, though I'm a mechanical guy, I'm leading a team which is doing all the controls. We have to have a closed loop control so that every feedback we get and we post process the data. We are also trying to involve AI and machine learning approaches so that we just close our eyes, we just press the damn start button, and the process should start running on its own. Okay, because if I think of building a part which is 2 meter height, I cannot be there entire day because the build time is 32 hours, 48 hours, 5 days. And therefore, it becomes very significant to have such approaches. For example, simulations. For example, your AI, ML, data driven decisions. So, and that's how the additive manufacturing comes really into picture because it's a completely digitized process. You have CAD model, which is digital. You slice it, which is digital. I cannot do it myself. If it is a rectangle or a cube you are printing, you can slice it. But if it is a complex geometry, let's say you have a nozzle, rocket nozzle, you have a propellant tank, which are some of the applications we deal with, you really cannot slice it. So that is also automated. After the slicing, you get a post-processing technique, which is again completely digital. So every stage is digital. You don't have any mechanical setup. Yes, one thing is, I'll just admit somebody request. So one thing which is manual is just I have to put a plate and powder. That cannot be digital because I have to give material. So because each aspect of the process includes digitization, it becomes more and more easy for us to get the data back. Uh, for example, I can have at what time, what was my position, what was the temperature, what was the gradient. I can just manipulate the time and temperature and time data. I can get the cooling rate also. So that way I get every data, and I'll just show you some of the study what we have done. So coming to metal AM techniques, there are so many, classification. If you go to the standard classification, there are so many techniques, but I would rather, focus the two major. So especially if I think of industrialization, right now, these two processes are the key processes. One is the powder bed fusion, which is also known as PBF. And if your source is laser, or it can be electron beam, right? So the usage is quite simple. You have a reservoir. Okay, so reservoir here. This platform goes up by a determined, distance. So the powder comes up. This roller starts to roll and spreads the powder on this particular platform. At the same time, this platform also goes down to accommodate the same amount of powder, and then you scan over it. The laser will just continue to, scan as the planned path, and then you get. So this will keep on happening in layer by layer fashion, and that's how this process works. It's called LPBF or EPBF, electron. Moving to the next slide. This is my interest, and I've really, almost from 8 years now, I've been working on this process. Here also you have source. If you talk about, you have electron beam, you have, let me put my writing pad here to me, and then you have laser source, or you are going to have these days, this process called VAM. So instead of, because you have a metal, and it can be in wire form or it can be powder form. So you have to melt either powder or the wire. So you need either electron beam, you have laser, or you have VAM. Now choose selection of this again depends upon the characteristic you need and the money you have. Okay, though I'm a PhD guy, but right now I mostly deal with business. So money will definitely come in my talks. So electron beam, usually machine will go 10 CR and all, but your quality, your thermal gradient, by default, your residual stresses are going to be very low. Laser, typically, 1 or 2 crore, 3 crore, 4 crore, it goes like that. So in laser, you have gradients, but again, there are solutions to that. These days, VAM, money, you can build a VAM machine just maybe 50, 60 lakh rupees. And you can have, because essentially it's a laser source. Oh, sorry, a welding source. I would say it's essentially MIG welding, right? So in this also you have the same process. You have GMW torch or even plasma arc, or you have laser beam or you have electron beam. So the process is relatively simple. You have the laser beam coming from the side, you will push powder and they will get melted over here. And then you move the deposition head or the table any relative motion. And you get the deposit over and over, like that. Okay. So that's the quick introduction of the metal EM technique that I deal mostly, almost daily with this process. So just to show you what I have just explained you, it's a YouTube video. Let me just play it. Let me make some space. So you can see you have a powder coming and through the center, laser is coming and it melts it. So you can see the powder is coming through the nozzle, it melts it, and then you get the deposit. Okay, it's as simple as that, but don't worry, there are a lot of intricacies in between when it comes to the actual process. So I'll more specifically talk hereafter about DD process. And when it comes to the current status in market, there are different focuses which people are, different sectors are looking into that. For example, R&D, and this also helps you to, especially the academia, to help identifying a good area to work upon. So the R&D center labs especially, their primary focus should be the identifying AM parts. The biggest challenge is there are processes, even we face this problem, what part to build. So that's how this collaboration is very important. Right now, if you see, there is a partition here. So both are incomplete. This industry cannot go without academia. Academia cannot go without industry. So there are different things like the R&Ds should focus to identify AM parts, because most of the research, what is happening, if I say daily publishing, right, I get a lot of alerts from Size Springer and all. I see they are mostly towards optimization, like they are just optimizing the process parameter by making some cubes or cylinder coupons, testing them, tensile test, high fatigue test, all those stuff. But one is the lagging part, which the R&D centers to also look is to identify build part, because I have also experienced, like when I did my PhD, was I have mainly built text coupons, but though it was slightly repair side, I got opportunity to repair some of the real parts. But when I see the other works, I feel you have to identify AM parts, and then you should try to work on them. Then they identify challenges with existing techniques. This is one important point. And then proper design changes suitable for AM technique. Now, after you identify a part, there are two problems. This is my personal experience. I also face some parts, they were being made conventionally. So they were very difficult to make with that way. And there are some design challenges. For example, there is one hemispherical tank ISRO uses. Okay, it's something like this kind of tank. Now, initially, what they used to do, they used to take a flat sheet and they will bend it over and over and over by means of forging. And then over the time, it becomes like this. And then they will weld it like this, okay, bottom. But now with the 3D printing, right, I can just directly tilt this part and build it, even though and then I can add some more intricacies on the surface also, some sort of fins for better heat transfer, or I can make it thin and adding some sort of cladding on top, which is very hard. So now the technology has driven. So the design also need to be adapt to the new technology. Then also the R&D should also work in testing and validation criteria. just what we do in the academia or R&D centers, like we just test it. But we should also find an application and think of how to build this thing. And also the central laboratories, they can even grant, to industry or academia back to, fund this. Coming to the institute responsibilities for the end users, aim development, process development, optimization. Definitely, you have a lot of maths involved. Materials, identify new materials, a lot of mechanical characterizations, post-processing developments, creating awareness in industry, because you won't believe right now, even still people, a lot of industries still, they don't know about 3D printing, and then have patents and publication. So this patents and publication will mostly come when you have a application oriented thought process. Essentially, otherwise, if you just do the process optimization, the existing, you can't identify. So now coming to industry. Now industry should identify parts for AM. That's same as list down the existing challenge. Industry should also, the biggest issue which I face is people are not accept it's definitely expensive. And yeah, another thing is these techniques, they have certain parts. Let's assume aerospace. They have a very critical acceptance criteria. So they are not ready to change. And if they change also, their existing solutions becomes obsolete. So that investment, and that's all. That's how don't accept it. And then opening doors for academia, service bureau, application, and support. Back and forth is required. Coming to service bureaus. So there are 4 types. So the service bureaus, which are currently, they should have a realistic. They are the guys actually work really hard. I should appreciate, and they should do DFM, design for manufacturing, because these are the guys who actually, okay, post processing techniques they have, and certain strength, certain structure, porosity, and post processing techniques, and then at the last, business of that's for their survey. Now coming to the point of the driving sectors, so you can see the images are converging. So these are as per their, I would say, total business. I can't give numbers, but how the business comes. So the majority of the companies are space tech. I have tried my best in somehow, have facts of, and guys are that doesn't work until this part, the part has to be then mainly not guys. Refurbishment is one of the application. When it comes to marine, definitely here also have shafts to repair, on line shafts, blades, all those stuff. Nothing much with respect to manufacturing. Repair and refurbishment using daily process is one. I would say if you can crack that some, it's a good business opportunity, especially for going back. The defense comes to the next because they have money, so business, and also they are attractive companies, and also they don't have much work. So it's all again when I have to demand. Whenever we have, that's the place I feel is really. So I'll move forward. So these are some of the examples. So the first I already played. So there are someone so this is called a bank. Usually and is made of 6 mm. There are so second, and at this point, a nice tech such parts. I think has facilities. This another application is the aerospace. So this part is inside. Outside have 7 6, and inside so a GM the layman language. So you can have such parts easily, and this interface, as you can see, runs through the part. Now there can be otherwise. Coming to the next application, this is one here some time back. So what I'm trying to show is there is RPM. This was just find engine process and how. So just to this and scan action face lock. So this engine application you have an existing want to improve.
The voice is not becoming.
Anything? Okay. So the next is a feature addition. So as you can see, this is an existing part. On top of it, this kind of this, you can say cladding is kind of being done. So you have an existing part and you want to increase its strength or you want to increase its heat transfer. So you have to add additional area. So 3D process becomes very handy for depositing on existing parts. So remember, when we say 3D printing, usually it refers to parts. But 3D process, I think, which is one of the 3D printing process which cannot feature addition, and that was one of my PhD using 3D process for repair and feature addition applications. So challenges in metal AM process, and why I'm telling challenges in metal AM technique, because once we know the challenges, then I will tell you how the simulation and digital twin, these kind of modern techniques, I call it modern techniques, will help us to find more solution, better solution. So the first thing is the process instability and defects. As these processes are evolving, we get a lot of these processes are even yet to be understood. Earlier, if you know, these processes, like let's say you have a shaft, and you are doing some sort of laser cladding. So these techniques are very old. But someone may get doubt like how the cladding and DED is different. So when we do cladding, I'm just coming to this point. Okay. So when you do cladding, you just put a one layer or maximum, let's say 2 layers on top. So you have your base at certain temperature and you quickly deposit layers and you're done. Just do some sort of machining with the GD&T of the part. But when it comes to DED, we are building the part. So you have a substrate at the bottom and you are depositing kind of, almost like 100,000 number of layers. Now here you have only thermal histories. You have layer of this temperature and you have layer of this temperature, and you're done. Okay, hardly it takes a minute, 5 minutes like that. Here your build time is 40 hours. Now imagine how much temperature data I have to keep in mind, and I have to maintain the same temperature on all the layers to have similar mechanical properties and similar temperature history. So if I don't do such things, it will lead to process instability. So what happens usually, if you don't control the process nicely, if you're building some wall, it will keep on becoming thin thicker. You will start with, let's say, 2 mm. After 100 layer or so, you end up with 3 mm. So these are the kind of issues that I refer to as instability and defects. So how the simulation and digital twin is going to help you with this is, one is we can do simulations prior to running on actual machine. Okay, I'll show you some examples moving forward. So instead of doing it on machine, because these are all expensive process, your powder is expensive, your process, your machine running cost itself is expensive. So it's good to have a thermofluid simulation or a thermomechanical simulation. Again, it depends how much intricacy you want. Run it and check it. How is the temperature increasing layer by layer? So this is how the simulation works. Moving next, digital twin can also help us have a real-time monitoring. Now, this is one of the interesting topic, and if this can be cracked, you can build a nice product, and we can sell it off and become well in a very short period. All right. So even we are working on having some black box kind of things to this. So what is real-time monitoring? It's like every layer I should keep tracking temperature. Okay. And let's say I need, let's say I'm doing SS and I know I should maintain 1500 degrees each layer. On next layer, let's say I got 1600. Like this, every layer I'm getting more and more, and that is why it keeps on increasing. Your width will keep on increasing. But if I have a closed loop monitoring, it will check. Okay, and this I have proven. I have done in past this particular project. It is successfully running also. Okay, so what we have done is we have used a pyrometer, get the value here, and this pyrometer will send an analog signal to laser. Okay, this this is increased, so it has to come down. So drop the laser, and it will drop, and this all happens within a time of 1 microsecond. Okay, so it will sense as soon as it increases, it will bring down. As soon as, let's say, it bring down, again it becomes, let's say, 1490 or something. 1490. Again, it will send the signal. Again, it will increase. So that's how it keeps hunting. I would say it keeps hunting. So if this is my set value, let's say this is 1500, it will keep hunting and try to, bring it to a value, and then it keeps becoming narrow. So it's a very proven product, and it all goes with a closed loop monitoring system. And with that, I will make sure that over and over, my temperature on the layer at every point, because the read and write is almost like 1 microsecond, maintains it there. So that's how the digital twin is really helping us. Moving next, we have thermal management and residual stress. Thermal management, I already explained. We have to, when you have so many of heat coming into the 3 watt, kilowatt, 4 kilowatt of laser coming in, the thermal management becomes more critical. And that is how the laser welding and a DED is different. In laser welding, we don't do heat control, because I have to just make these two plates are there. Okay, just weld it. That's all. I need not to come back on this layer again. And that is what happens in DED. And that's how I told they are different. Then next comes the residual stresses. Now, this is one of the key, issue with any DED process, and any 3D printing, I would say, because we deposit layer by layer, and there is a solidification happens. So the previous layer, when it is solidifying, it try to contract back, and the heated layer, which is coming on the top, is expanding because of temperature. So one is so this one is trying to shrink, this one is trying to expand. So what happens? One is telling I'm shrink, one is telling I'm usually this leads to crack. Okay. So have lamination issue. But if not here, your part is weaker. So these all things, and then how this simulation and digital is having finances and some sort of mechanical analysis where we should fully cover and solve temperature, send this temperature to the mechanical and your displacement XY. That is one. Then there are also digital essentially have heat. So once we have same heat in stresses, that's stresses. Process parameter, I think it's quite obvious. We can instead of doing very expensive 64 experiments, I can give you in just one shot. I'll just explain how I'm really sorry I cannot show you some pictures, but they are they have some sort of disclosure. Such. So let's say I'm doing SS. I know this melts at 50 Celsius. I have a closed loop system CLS, and like I explained, so I have a display and I have a laser coming, and just next to it, I have so laser is coming. I have essentially temperature, and it gives me feedback. See, there I have some something that's again IP. Yeah, so I can't detail. So what happens? And then the system. Then have C. Essentially, a PLC has because the laser signal. So if you 0, and if you signal max so what I do is like I will set well. You see, I know this is it. I will set initial, let's say on PC one and certain speed. This I can take for. I don't know how is this for this temperature. What I'll do is I'll just run at a certain speed, and as I tell you, this is the set, and let's say I so it will keep running at certain time. At this time, when it is coming in line, I will the laser. So that is let's say it is 950. So I started at what I'm ending up at 950. So I can. This is the power where I should work.
Dr. Chaurya, your voice is in between connecting, disconnecting, connecting, disconnecting. Please check it once.
Okay. Let me try some other way.
No, it is fine.
Now is it okay?
No, it's fine.
Now it's okay? Now it is okay. Can you confirm?
Yes, sir. Now it's fine.
Okay. So I'll just move mic a little aside. I think it's moving. All right. So that is how I find a correct parameter. So there will be someone who will be doing a grid of lot of power, scan speed, all the stuff. But this is one, I would say, a very easy way. So you give me any material, I will find process parameter maybe in 2 trials or 3 trials. That's how we do. Because industry we don't get time. That's thing. So using ML model, I can easily solve this process parameter optimization. and using digital twin. Now you are hearing simulation and digital twin again and again. I'll come back to that, what it is. So lack of real-time process monitoring and control. So I think most of the machine in India running currently, to best of my knowledge, none of them has a real-time process monitoring camera. Okay, camera or a hardware, even a pyrometer. I really don't think of anyone has. Maybe someone has developed in-house, that's different. So that's what I was telling. In situ monitoring is very important. So one example I have given you is having a laser and then looking the value through a pyro. This is one example. Another example could be having a laser. In real time, I should have a camera here, just optical camera, CMOS. Okay. And I can, I should have trained some model here, AIML model, with lot of images. I will tell if somebody is depositing, let's say track like this, if it has some holes, it's a defected part. Okay. If it's a discontinuous deposit, a big, small like this, it's I can say energy not sufficient. So different, I can give different constraints to it. Definition, I can give so many images, how energy this will look like. So it should. So this is a camera based. This is pyrometer based. So there are different techniques. So this is called actually imaging. It's imaging process. So I can use high speed imaging, thermal sensors to, control my process. So from here, if I see this kind of projects are coming, I should immediately inform my laser system through a PLC. Okay, always there is a PLC to increase the power. Okay, if it is over depositing, I should interlock this with pyrometer also, that now you're overheating. So this is called the complexity of a system. Me being a hardware integrator, right? We are essentially a hardware integrator. We don't spend much in R&D and all. We mainly take hardware, CloudWall sensors together and build a product. That is our motive. So we do a lot of this kind of stuff on a day-to-day basis. Moving next, material behavior and microstructure evolution. Again, this you need some sort of phase field modeling you can do, and you can predict. You can do even finite element analysis of your process. You can get thermal gradients. There is something called G by R, G into R. There are ratios, gradient by cooling rate, gradient to cooling rate. All those, solidification rate. This is called solidification rate. With that, you can predict what is the kind of grain size you can expect, what is the kind of microstructure you can get. And anyway, you have more complex phase field simulations, Monte Carlo simulations that can even give you grain orientation also. That's not a much of part that we really look into, because we mainly look for microstructure. Usually when industry asks us, they really don't ask what microstructure they need. They tell, I need this much hardness, this much strength. They don't bother what microstructure you are getting, whether it is alpha, beta, and titanium or whatever it is. Are you giving me this much ductility, this much strength, and this much hardness, and surface requirements? That much they really bother. So that's how. Then build features and low repeatability. Now repeatability is one of the key problem when it comes to any DD process or even any 3D printing process. Polymer to some extent, I would say, they have kind of attained a position where they are really repeatable. You get printer for 40,000-50,000 and just plug it, you get the job done. But when it comes to metal, especially with DED process, you have every layer, your temperature is changing if it is not monitored. So every previous layer has a different thermal history. All right. So your chances of failure is too high. And also repeatability is also difficult. For example, if I'm building, I'm tracing this path. Okay, let's say it is 2 meter by 2 meter. Okay, now if I start my laser from here and if I travel like this and I came back to this point, let's say the total time to cover this is 2 minutes. Okay, Now in 2 minutes, this point is now cooled down, almost cooled down. But let's say the same geometry, which is at lower scale, let's say it's 200 mm by 200 mm. Okay. Now, because the material is same, I have to deposit at the same power and scan speed. Now I reach here very like, immediately, I can say. So let's say within 30 seconds, I came back and it did not get sufficient time to cool down. So the same process parameter, if the geometry changes, remember, not material, just the geometry changes, will not work. So that's how the low repeatability issues will come. I cannot have same process parameter every time. So in this case is what happens, I need to give an interlayer delay. After finishing one layer, I will ask laser to wait for some time, then again do the another layer. So that's how it goes. And then definitely sustainability and material efficiency. Definitely we have to leave something for the next generation. So we have to use everything sustainably, and we should utilize, for economic benefits also, economic benefit of country as well as the honor of the machine. It's very important that we should utilize these powders carefully, and so that we have high deposition efficiency, then only it is possible. Okay. So now coming to understanding the key concepts, simulation and digital twin. So simulation essentially refers to something like, these all, whatever is written that anyway we have explained, something is like you have some physics, okay, and you try to replicate it in a very simple way, and there are ways to do it. One way is analytical modeling. Okay, you use governing equation, you solve them. Okay, it's called analytical modeling. People usually do this in MATLAB or Python or C++, any preferred language. Coming next, you have finite FE approach, okay, finite element. You have finite volume. You have finite difference, finite, FDM, and then you have, and there are so many techniques moving forward. So you kind of make a model which is similar, not of the machine. Remember, it's not for the machine, it's for the process. So you have a physics. Physics belongs to a process. And you try to understand that. And on those predictions, you make judgment. You see, it's these FE approach, FV approach, finite volume. They are already numerical approaches. They have already some sort of error. If you use this data to train AI or ML model, definitely you can use, there is no problem. But these models have their own like 10, 15% error, 20% error. If you use this model to train AI ML data, that again will have problem. So it will become like you have a garbage bin. If you put garbage inside, only garbage will come out. Okay, so that's why people avoid using the finite volume, these data, even analytical modeling also, because analytical modeling also have so much of simplification. Otherwise, you can't solve really, you can't really solve this problem. So to avoid such things, people bought digital twin into picture. I'll explain after some time. So a typical roadmap for simulation goes this way. So you have to have a physics, as I mentioned. It can be thermal, it can be mechanical, it can be a fluid problem, or it can be multi-physics problem, which means combination of these. For example, a DD process is a multi-physics problem because you have lasers hitting a material, okay, hitting a material, not heating. That laser will heat up the material, which is a thermal problem. Because of that heating, the material will melt and there will be a lot of vortex, Marangoni flow, and all those things. So you have a fluid problem also coming into picture. And because you have a thermal, there will be thermal expansion and contraction because of the thermal coefficient. So you have some mechanical response also. So that's how a simple problem, a simple cladding process that you look happening has a multi-physics behavior. Even not these three, then you have microstructural also coming into picture. So once you are defined with this, then you move to the boundary condition. Then what kind of heat input you're giving, loads, constraints, whether how it is fixed, then material properties. Now, depending upon a thermal problem or mechanical or a fluid problem, you have to define your thermal conductivity, Young's modulus. If it is fluid, you have to define viscosity, surface tension, other things. Now, once you define a problem, then you come to the pre-processing stage. So you have to create your geometry. You have to mesh it depending upon what method you're using. Then the material that you decided here, you have to bring it back and assign to the model. And then again, whatever boundary condition you identified, that you have to apply on the model. Okay, so this all interlinked. Once you have done everything, then you move to the solver part. And here, literally, you don't have to do anything if you are using a standard package like ANSYS, Abacus, COMSOL. They do the job for you. Okay, this assembly of global metrics. Then you have time stepping. Time stepping is a critical point that you have to define. Let's say every step you want to solve 0.01, 0.13. Now this time again depends upon the convergence, like how fast your simulation happening. For example, if you are doing a fluid simulation, current number, I guess I did some time in PhD, so current number is the factor which decided what should be your minimum timestamp. And then you have to also decide whether it's an iterative solution and what is the convergence criteria and residual reduction factor and all. I don't want to go much into this because it's a long thing. It's a long thing. And once everything is done, you will store the data. And then in the next step, you call that data and plot it, understand it. And then last, most important thing, you have to validate the model. If you are getting right trend or you are not getting right trend, this is the most, I would say, painful thing, most painful thing. Because anything goes wrong here, you have to come back to the basic again. All right. So there are three types of simulation when it comes to metal AM techniques. One is the process simulation, build failure simulation, and optimization simulation. Layer-wise layer deposition modeling. I will show you one example moving forward. Particle flow simulation, how the particles are falling, whether after hitting they are not going away. So how much you are throwing, what is the particle size effect. These are all things you can simulate. Heat transfer, material flow, microstructure evaluation. I'll just show you some of the example I have done past. Then when the build field simulation comes, there your main concern is residual stresses, whether you are exceeding yield strength of the material or not. Essentially, if you're increasing that, you're leading to cracking. Porosity simulations, again, fluid simulations feel best for this. Then you have a mechanical behavior under different scanning strategies. So you can also, if you have a material and you're filling it, how you're going to fill this, like this, or you're going to fill it this way, or one layer like this. This is one layer. Second layer, you are going to fill it like this. There are different ways. We call the scanning strategies. So that is all these things and their effect on the heat transfer. Everything can be studied. And then at the last, you can vary process parameters, scan speed, powder feed, wire feed. Again, you have so many models here can be done. Moving next, if you come to digital twin, now how it is different from simulation? That's first thing we should understand. See, standard definition, I just don't want to read it. You can read it, not a problem. Let's try to understand with this flowchart, okay? See, in a digital twin, as you can see in the definition also, you have a mention of physical system. So this is the physical system. So it is very important. See, in simulation, I need not to have anything. I should only know what is the physics. If it is a laser welding, it is an arc welding, we have an arc, we have a volumetric heat source. So these all things I have to study. But when it comes to digital twin, now twin means like you have a second baby, right? So like a second baby should be a replica of the first one. Okay. So you need to have a physical baby with you. Then only you can say that you got twins. You cannot just imagine, right? I got twins. So that's how easy it is to understand. So you have a physical system and you kind of, create a Similar system in PC, but remember this. Now one can ask, physical system, I can make a CAD model also. Then how a physical system and a CAD model is different? See, in the digital twin system, if you are moving your axis, let's say in X direction by 10, in model also, your axis should move by 10 mm. So it's the exact replica of a system. Now, if I have moved in my machine 10 mm, or if I have fired the laser, let's say 2 kilowatt, how my computer will come to know? It will come to know through the communication only. For communication, I need to have a communication protocol. It can be Profinet, it can be Modbus, it can be practically any communication, Ethernet, TCP/IP. So many protocols are there. And one side I need to have sensor detecting the data. So a relevant sensor, your temperature, you need parameter. You need some sort of camera. I mean picture, you need camera. It's as simple as that. Some IoT device. IoT stands for Internet of Things. So like we all are connected through WhatsApp, right? So this is a kind of IoT. So all mobiles are connected, all machines are connected through internet. So it's Internet of Things, to be telling you at a layman language. Then some sort of AI model and some real-time analytics. So these all data we have to feed to this CAD model. Essentially, this is a CAD model, it's a CAD model only. There's no difference. But only which makes it different is this value will manipulate this CAD model. Okay. So as I mentioned, if I'm moving 10, it will move by 10. So, and it's not like it's data is traveling this side. No, it happens the other way also. So I can move my axis by 10 mm and I can check what will be the response. I can make my kinematics, you have 5-axis motion and all. I can check whether this part is buildable just by running the machine in the virtual machine. Essentially, it's a virtual machine. No need to bring part here also. I can try it everything. I can give you a real prediction. In this many hours, I can build this part for you. Again, I'm talking with the industry perspective because I have to give you a time, right? If you are my customer, okay, sir, I'll give you part in another 40 days or 30 days, like that. Since I'm getting this data into my model, I can use that data to train some sort of AI ML for process optimization. Let's say I'm doing some kinematic simulation. I find that when the radius is coming, my head is getting slowed down. So I can tell my model whenever this is my set value again, and you should increase or decrease it accordingly. You have to maintain it same. So the model should increase the speed in the actual model. That's one example of the implementation we are doing even right now. Because usually what happens when you are turning, you're making a sharp turn, it kind of deaccelerates and suddenly accelerates. So all those things we are trying to avoid. So why we should use digital twin in additive and what are these applications? These are some of the example. I'll just quickly cover. Let me just see the time once. So we have another 20 minutes. So one is definitely the real-time process monitoring to detects before they happen. So we have to kind of find, right? If laser power goes this much, defects may arise. If speed goes this much, so we need to have some sort of back data. I need to have some sort of information. If picture is appearing like this is going towards that, correct it immediately. So this all thing happens at like 1 micro or 10 microsecond. This all correction has to happen. Predictive maintenance, let's say my motor torque is increasing over let's say if I plot 365 days curve, my motor's torque was initially, let's say T1, and I'm seeing over time my torques have gone high to a value T2. I can also trigger a value when the torque reaches this value, which means call for a maintenance. Okay, I should not take any. So my motor should have a dynamometer kind of thing, which should keep identifying the torque is increasing, which means my machine needs some sort of torque, or it need not to be necessary that I should do with torque. I can use even electrical also. I can find for same operation earlier my machine was taking, let's say 20 kilowatt hour, 20 watt hour. Now it is taking 30 watt hour, which means my system got some sort of resistance. So I should correct it. So that's how also we can call this for predictive maintenance. Process optimization, very obvious. So many people do this. Reduce waste material. So I should have prediction before the part is about to fail. So I can place some sort of vision camera on top. Keep measuring. Let's say my part requirement is the part should be 6 mm thick. Okay, and I can set a value in my vision camera. Don't let it exceed 6 mm. If it goes high, reduce the power. I can command it like this. So what happens with that? I'm actually reducing my waste. If I was not using that system, I would have got 8. Again, I have to machine it. I have to do some sort of post-processing. One of the key things which we should do is the faster certification. So if we can test the process virtually and I can implement it in a real machine real quick, I can also reduce my physical trials and I can get certification for parts very fast. When I say certification, means my process parameter, window, whatever it is there, it should get certified that, okay, this is the right technique to make this part. Okay, it's again part dependent. Certification is always part to part. So the application is melt pool monitoring, real-time defect detection, residual stress predictions, multi-material deposition tracking. So even by color also, I can put a camera, I can detect whether copper is being coming or SS is coming. So again, it's how we think we can manipulate this kind of software. And again, closed loop adaptive manufacturing. Again, I explained you. So, okay, this anyway we have covered. So these are some of the examples, process simulation, how it looks like. So you can see it's a very simple model and there is a heat source moving and you can actually plot, the temperature, like how from center to how it's reducing. So all these things can be plotted. This is one DEM, discrete element modeling of a PBF process. This is essentially a PBF as I explained in the starting. Need not to be LPBF, it can be PBF process. So how well your powders are being, deposited. This is again thermofluid simulation, okay, of a PBF process. You can see the bead width, how much you're getting. Those all things you can predict, even what is the temperature you're getting. So you can see it's kind of 400 Fahrenheit. So again, build failure simulations also can be performed. So as I told before, right, you will have some cracking, delamination kind of things. So with the simulation, we can have idea like where all the delamination is going to happen. And we should take special precaution at that, or we should add some sort of extra material there so that the material, even though it comes out, we should have some sort of, making some arrangement to just rectify it. Optimization process parameter. So this is a typical conventional way of doing process parameter optimization. So you'll have some bad process parameter, no deposition, and then you will get some sort of good process parameter. So similar thing can be done using some sort of analytical modeling, and you can predict what is the height you are getting and all those stuff. So I would like to show some of the work that I have done. I'll go real quick, sticking to the time, 15 minutes, I think more than sufficient. So thermal modeling and ED process. So the methodology goes this way. So you have to select a physics, which is for a DED process, is a thermal problem. So since it's a thermal problem, heat conduction equation. So we need to define what is the material density, what is the specific heat, and what is the thermal conductivity. Again, material property depends upon the physics that you are selecting. And if you see this graph carefully, I'll just zoom in. You can see these are temperature dependent properties, which means, for example, density, you can see black color is coming down as the temperature is increasing from 0 to 1600. And most of the software like ANSYS or Bacchus, they offer this kind of features. Otherwise, you have to write a UDF, user defined function. So this was the model that I used. I choose the right type of element. Again, I don't want to go much into that. Usually it should be a thermal model because obviously we are doing a thermal modeling, meshing, and then you have to define boundary condition. For example, initial temperature is 25 degree. You have convection at 10, which means it's a still air. And then you have uniform temperature at the bottom. Okay. So I'm assuming my bottom should always remain at 25 degree because I am simulating a very big plate, but a small model of it. So I assume that my plate has an infinite absorption of heat. So that's how this boundary condition works. I will solve it and then I'll get some result. And for DD, we use a technique. It's a very old technique I use in my PhD. It's called EBD, element birth and death. So in this, we program it in a way that the heat source is moving, and as soon as it moves there, we turn on that element. So when I say turn on, we bring its characteristic back. So initially we define it has a infinite thermal. I mean, on a simplest mathematical way, I would say we tell the model not to respond to any boundary condition. So it will not be counted in any mathematics. But as soon as the heat source comes, we will activate those elements and then it start participating. So this is one example of NSYS work that was done. So you can see we have simulated kind of 5 lasers, 5 layers. So one thing that you should see is layer 1, layer 2. So here if you see, the starting was at this height and end is here. So when we plot it, we figure out the melt pool depth, I would say this is length because the laser is moving this way. So it's kind of increasing. Okay, we did this for 5 simulations like this. And also how the peak temperature is increasing, that also we could get it at one number layer 1. It was around I would say 2870 something. And after 5 layers, you can see it is around 3125, something like that. So these all kind of predictions we can do. Now I know. So even if the time permits, I will show you one study I have done. Further to this, we have used this data to train a AI model and tell us how much power we should reduce at every layer to have this melt pool length a flat line. It should not be increasing. It should be a flat line. I'll just quickly show you that also. So again, this is data, and what we are trying to do is we are trying to plot it with different scan speed just to identify whether the model is working correctly or not. Okay, so this trends is at par with the physics. Remember, I'm not telling experimental, it is at par with physics. So if I'm increasing my speed, consider this one. Okay, if my speed is increasing, definitely my depth will go down because my heat energy density is coming down. Okay, sorry, I'm increasing speed now, so E will come down, denominator will be higher. So nothing much to show with results. That's not the intention of this talk. So same way we have done with a number of layers. Temperature also we have predicted, as I told before. We have also considered calculating cooling rates from the data. So you can see as the speed is going high, the cooling rate is increasing and the gradients are coming down because your temperature is getting less. So this is what I was trying to tell. This is how the simulation helps to understand the physics behind the process. Now we have also thought of studying what is the effect of remelting, because once you have deposited one layer, you have again depositing another layer. So what happens, this temperature will be a number, it will go down, again it will come back. How much it is coming back, we also thought of getting an idea of that. So this is the curve, you can see the black line. If you see initially your part is at 25 degree. When the laser came, it hit almost 2800. Okay, it was cooling down. Black color line, see carefully, it was cooling down and it almost came to room temperature. I would say 100 degree, not room temperature, 100 degree or so. Suddenly, when I started depositing second layer, you can see the black color. Let me zoom in. Black color line again went up. Again, it became cool down. Again, when I was depositing third layer, which means the blue line, you can see the black color line again went up. Just count black color line. Again went up. Again went up. So this leads to residual stress. Okay. The more it is happening, okay, just put it this way. So like this, like this. So every layer you have some sort of this. So you see, I need not to do machine. I need not to have any machine to understand different characteristic of the process. Now I will show you quickly thermofluid modeling of the process. So this is one published work of my PhD. So we thought of, see how the fluid flow will affect the melt pool depth and all. So we did one numerical study where in one model we consider only heat transfer, and in one model we consider only heat transfer with fluid flow. So this is the way. So we did 9 single tracks. We did some characterization. On one side we took finite volume method because I used ANSYS Fluent to do this, and we did fluid flow and without fluid flow. We did the comparison. So this was the demelting thing. These are the all tracks you can see. Okay, and these are the cross section, SEM cross sections of that. So before I did on ANSYS Fluent, as I told I did a grid independent study. So how much number of cells to have here. So you can see. So I as I remember, I used this point because here to here there was hardly any like 3% or 4% difference. So, and if I count time, if the simulation takes here around 30 hours, here it takes almost 70 hours or so. So result wise, there is only 2 to 3% difference, but time wise, it's almost like, double, more than double. So I sticked here, I remember. And this is the Gaussian heat distribution model for to replicate laser. And you can see almost very small geometry. This was a very small geometry, I think maybe some 5 mm or so. But you can see in that 5 mm, yeah, you can see 11 mm, 2 mm, 5 mm. And you can see how many cells we have. Still, it is less, I would say. These are some of the continuity equation we use, some momentum conservation equations. I'll not get into this right now. And these are all heat equations. And this is the Gaussian laser distribution equation. Some mechanical properties, material properties, I would say: liquid is temperature, solid is density, specific heat, thermoconductivity, latent heat of fusion, dynamic viscosity, temperature coefficient of surface tension, d gamma by dt, and thermal expansion coefficient. So these are all values. And this is the result. After doing all this, we get this simulation running in ANSYS Fluent. I'll just show you some of the post-process data. So you can see, leave all these tables and all right now. We are not much bothered to this. You see here. First, see when I run simulation without any thermal counting fluid flow, you will see it's just a simple, half circle, you can say. Whereas this actual surface is something contourish, it has a contour here. So if I move here, you can see if I consider fluid flow in my simulation, this is with fluid flow, you can see how well the process is being traced. So this is the this indicates why it is important to consider fluid flow effects in your model. So this was the whole intention of doing this, and also we try to understand how the fluid flow, let me draw it here. Flow will happen. So for this material at this temperature, it will flow like this. So it will lead to deepening of the melt pool. Some process, if your temperature is not exceeding, it even goes the other way. Okay. So in that case, your melt pool will be more or like this, wide, not much deeper. Again, it depends upon Marconi flow and your material purity level also. We also predicted with the model, we calculated G into R, which is essentially cooling rate. And with that cooling rate, we predicted the values. So these are the values, and these are actual values. These experimental values we did, okay, and these are the values. So you can see how close they are with respect to the model. So you can see the FD model, which means fluid dynamic model, is giving much better results than the HCS model alone. Again, some simulation stuff. We plotted G into R versus G by R. So G by R gives us the how your structure will change. So cooling rate essentially gives you indication of how fine or coarse is your microstructure. The G by R gives you indication of morphology. You have equiaxed grain, or you have dendrite or whatever. Okay, so we plotted and we got very convincing results. Conclusion, I'll just leave it for time being. Then this is the process parameter optimization. We did one more simulation work. Here the intention was to predict this. I already explained. Here our intention was to predict how much bead height. If I say this is my feed rate, this is my power, this is my speed, what will be the height and width I can expect? So these are my objectives. I would say X and Y. Okay, so I used the approach called enthalpy approach, and how it works is, let me quickly explain. So we have a heat. So what we do is, as soon as this heat transfer occurs, and let me put it this way. So as soon as we put a laser here, okay, as soon as this will give heat back to the top model. So this is the mesh, actual mesh. Okay. So when I first apply the laser, I will deactivate these. And how I will activate is, I will activate one row first, and this will do some heat transfer. If the enthalpy at this layer, okay, these nodes essentially, it doesn't work. FEM works only with the nodes. At these nodes is more higher the enthalpy of the material, which means it's in melt state. Activate those. So like this, we will keep activating, and we will finally get a contour like this, until there will be one time when there is no enough enthalpy. Thereafter, we'll stop the simulation. This is how this used to work. So you can see how fine it is. You can see the mesh, how fine it is. So again, some material properties, some setup, some tracks we did, single track work. These are some experimental results of cross section, just to get these height. Then now these are the results. If you see how the model is calculating, so go back. I'll just go back. You can see this is the height which we were trying to predict, and this is what we get here. Okay, this contour essentially. So you can see as the scan speed is increasing, it is going down. It is very smaller. So this is what happening, and we also try to match it. If you zoom in, it's not exactly matching it. There is a difference of some microns here. Some case it match well. So you can see some of the results here. Just to tell you a conclusion, like the track heights, we had a maximum error of around 24%, and in width we had an error of around 21%. So I mean, say these results are too off. 20% is not acceptable. But what important thing we should understand is how simulation is helping us to understand the process, and at least to have a fair prediction. Say 20% prediction, I will not say it's too off. It's not like 120, or it's like it goes in negative. So, but it gives us the study. What's the time now? Yeah, we are almost close. I'm almost in the ending of stage. So this is one model we created using MATLAB. Okay, it's actually with a real PID controller and everything. I cannot give much details because this is ongoing work. So usually what happens to achieve same, width, as I told, right? I need 1.5 mm width. Every layer, my laser power, which starts from 850, you can see the model. Okay, it's not done by me. I kept power constant in experiment, but the model tells me reduce it by 800, reduce further, reduce further, reduce further, if you have to achieve this as straight. I told you like last time, usually if your power is same, this will keep increasing. So I want width, my feature to be remains same. So these are the simulations we did. You can see how the simulation is going here. First layer done, second layer done. And let me just show you the final result. Okay, these are the results which should really be, you should look at. So you can see first layer, when the power is constant, you can see first layer, this is the, I am almost covering 3 steps, 1, 2, 3. But when I'm reaching top, you can see my melt pool has gone bigger. It's almost this much now. Earlier it was only 3 steps. Now it is almost 5 steps. Okay. And when I did simulation back with the AI generated or the trained model, you can see it has told me reduce the power, keep reducing, keep reducing. Now what we did, we got it starting here, ending almost on the same location. So that's how, the training of the model is really helping us with this control element over here. This is the guy who does everything here. So that's how we go. So coming to future of AM, this is mostly last slide. So where we are going actually. So definitely a process which has so much of complication, it is good to have hardware. It is good to have some sort of controlling mechanism, because I can only think of one parameter. There are temperature, there is stress, there is microstructure, there is cracking happening. At the same time, motion is happening. So for those things, we need to have some sort of AI-driven simulations, AI-driven predictions to help us. Okay, I'm not telling it is going to replace an engineer, but it is to assist us. Then we should have a real-time adaptive process control. This is the, I would say, a must requirement currently. Then simulation driven certification and qualification, because the part, how much you optimize the process. I'm just telling at academia level, you tell this is the right parameter, this is the right parameter, unless those parameters are not certified by a third agency or the end user, those parameters are of no use. So we should have some sort of, technique or such an accurate predictions that people should just accept it. All right. So with this, I will conclude my slide that simulation reduces trial and error. Digital twins enable real-time process monitoring and adaptive control. And the inclusion of AI will definitely help us to come with better products and more human-centric, keeping our effort into mind and helping us indirectly. Thank you very much.
Participant, if you're having any question, please ask the question. Okay, Dr. Chaurasia, I also have one question.
Yeah, please.
Regarding this laser welding, the heat source modeling, you are considering by specific modeling like by conical model or some cylindrical model or some WLSI model, or you are combining some model in ANSYS?
Yeah, again, it depends. There are like, for example, laser, right? When we deal with laser mainly, I think Gaussian distribution is the best. Again, it depends upon your beam profile. For example, some machines will have square profile, top hat. In that case, your simulation will not help you. Your Gaussian distribution will not help. So, and again, if you're simulating a VAM process, there the arc goes through the metal. So there you need a volumetric heat source. it's not only on the surface. It has to be volumetric heat surface model. So that's how we choose a right model, and also it's in a trial and error, which works for a certain machine or process parameter. Anything, anyone?
Yeah, good evening, Dr. Surasya. The simulation I think you are doing in ANSYS.
Yes, ANSYS.
Are you writing any kind of coding for that?
Yes, even for the Fluent, I have written some UDF. Even for Workbench, we have written some UDF. I mean, it is must because if you count console, you have some sort of options like you have some model to make inbuilt Gaussian heat distribution. But when it comes to application specific like ANSYS program, which are general, essentially Abacus ANSYS are general purpose FE software. So we need to have our own macros written for such things. And also it becomes easier if you write now.
Yeah, the coding what you're writing, that is in like specified any kind of language like C language or any other languages are required, or
for example, different software have different. For example, if you use ANSYS APDL, it uses Fortran. If you use Workbench, it uses Python. If you use Fluent, it uses, I think, C or C++. I remember it is, I think, C only. Then if you come to Abacus, again it's Fortran. And then if you come to Comsol, they have their own language.
Sir,
okay.
Sorry, sir, I am Dr. Manish. So
Yes.
in while ANSYS, do you also use APDL language?
Yes. ANSYS parametric design language. It is. I feel if you are a researcher, it is must, and if you have interest in simulation, because I need not to do repetitive tasks again and again. I can just write a macro, create this model. It becomes really easy. Otherwise, every time you have model and all.
Click the button, all those things. While writing the code in APDL, if once write, you can edit it very easily in the APDL format.
Right.
And also, if you do it in the window, it will generate in backdoor APDL code.
Right. That is one way of doing. But certain things, right? For example, you have to make a Gaussian heat source. Those things you cannot do directly in backend. You have to write a macro your own.
Yeah.
Yes.
Sir, does your company also provide the internship to the student? We take a student?
It depends actually. If it is a longer internship, we can think of that.
Like 45 days?
I only have to decide, I am the guy who leads this. So maybe you can write to me, not a problem. I can think on it.
And for the campus placement, sir, because our college is having campus placement drive session now. I teach here in CPET Jaipur. It's all over India. It's about 45 institute throughout.
Okay.
It basically deals with the plastic testing. And here we are having 3 branches. Plastic technology, mechanical engineering, and petrochemical engineering. So for thing it suits the mechanical engineer guy.
Okay. Sir, I got one question for you. Please, Zubair, please pardon me.
Yes, sir.
Today I got one challenge actually. There is one toilet seat. There is one part actually plastic. I have to reverse engineer it. What is the best way to get what material it is? It's a plastic. I am not a plastic guy. I am a metal guy. FTIR is good, Mr. Manish.
What, sir? Actually, I also belongs to pure mechanical engineering from my BTech to the PhD. Okay. I'm also here learning some basic plastics.
Okay, that's fine.
What you can message me. I will ask to the expert guy who are here in the expert in this field.
Definitely.
Okay. Okay. Any other having question? Please ask the question.
Request to share the slides, sir. It will be helpful to all the participants because having basic of simulations, all those things.
Definitely. There are some unpublished content actually, and
So then you can delete that content if did that.
I share other things, not a problem.
Okay.
Hmm.
Okay. Thank you, sir.
Okay, if there is no question, then we will end the session. It's my privilege and honor to extend my heartful and out of thanks at the conclusion of this today's informative and engaging session, online session. And first and foremost, I would like to express my gratitude to our esteemed speaker, Umesh Khande sir and Chitan Chaurya sir for their sharing their valuable knowledge, insights, and expertise. Sir, your thoughts-provoking discussion and really enriched our understanding of the subject and inspired all of us. Special thanks to our all participant faculty members, researchers, and professionals from various prestigious institutions across India. And I would like thanks to my sincere appreciation to ATAL and my uh, Aditya University's technical support people. Okay, thank you, sir. And with this remark, I'm concluding the today's session. Thank you, Chaurasia, sir. Thank you so much.
Sir, I request Sir Chaurasia sir to share you the contact details, email ID and contact
Yes,
details.
yes, I will definitely take that contact detail from Chaurasia, sir, and I will share in group, sir.
Okay. Thank you, sir.
Thank you, Chaurasia, sir. Now I am ending the meet. Thank you so much. I'm sending the feedback link in the group. Please send the feedback as soon as possible.